G'day viewers. In this segment I'll talk about using cryptography to provide message authentication. Okay, so what we're talking about doing now is using encryption, but encrypting information to provide authenticity, to make sure messages came from the correct sender, the sender we thought they came from, they're authentic, and integrity. These properties often go hand in hand, making sure the message hasn't been altered. So often these are actually different properties than confidentiality. Often confidentiality of messages isn't enough on its own. So a little bit on the goal and threat model, just so we're clear on what it is we're trying to do. Our goal here is to let Bob, who just received a message from Alice, at least that's what he thinks. Bob would like to verify that the message really did come from Alice and that the message has not been changed in the network. These properties are called integrity and authenticity. And the threat here that we're trying to protect against is that Trudy, here in the middle of the network, will tamper with messages. You might notice I've changed from Eve to Trudy. Trudy, short for intruder, is an active adversary. So whereas Eve just listened to messages, she intercepted and overheard them, Trudy can interfere with messages. She can tamper with them, rewrite them, send messages of her own to either Alice or Bob. So Trudy is an active adversary. Now, here's one interesting thing. You might just say, well, wait a minute. We just did all of this unit on using encryption to provide confidentiality. That, really hid the message inside the network and everything. Isn't this enough? Haven't we really provided some of these properties that I just was going to talk about already? Well, the answer is no. Obviously, because we're going to go through them a little more, but you might wonder why it is that encryption isn't enough. Let's go through a couple of issues and so that I can just convince you that encryption for confidentiality isn't always enough to provide authenticity and integrity. In particular, let's just imagine, as a thought experiment, what's going to happen if Trudy, as the message goes by in the network, flips some of the bits. The message really came from Alice, but it's been mangled now in some way. Trudy's flipped some of the bits. Well, Bob will get it. Bob's going to decrypt it over here. And, at least he will apply his usual decryption operation with the key which he shares with Alice to the bag of bits that came in. And what's going to happen? Well, this will probably happen. Bob will receive some message. The ciphertext which was sent, any ciphertext can be mapped to a corresponding plaintext. So even though Trudy flipped some of the bits, that didn't mean that Bob couldn't decrypt it. He could still decrypt it and get some message. So Bob will receive an altered message. This is a little worrying. Trudy didn't read the message, but she still kind of messed with what Bob got. Bob got this altered message. Now, you can see this is a bit of a garbage message, and Bob is just saying, And you might think that it would be very unlucky that Trudy could mangle the bits and cause a correct message to come out. So it's probably okay. Bob can realize that that's not a good message. But this isn't always the case either. Trudy can be more subtle in terms of how she flips bits, depending upon the encryption scheme. So in particular, it's often the case that encryption schemes will work with blocks of data. They will encrypt a block of bits at once and then move on to the next bit. And depending on the schemes, we have to be very careful here. Suppose we have a scheme that lets Trudy reorder the messages. You can see here the message, here's the blocks. They should have been sent 1, 2, 3, 4, 5 if they're all one big message and they've been chopped up left to right if this was one big message. However, you can see here Trudy's reordered them. She's just, she knows maybe what the block size is because that might be well known as part of the algorithm, and she's reordered them. Bob will decrypt this because Bob will decrypt anything that comes in to see what's there. And what's going to happen? Well, Bob will get a message. Here's the message he happens to get. Buy now, do not stop. Okay, so Bob goes away and does it. But that's not the message that was sent because we've changed the order. What was the message that was sent? Well, let's just write it out. If we rearrange these blocks to be in the correct order, the first block should be 1, so that's stop. Second block 2, do not buy now. Oops, that's a very different message than the one that Alice sent. that Trudy has somehow managed to happen. So we're really not going to want to allow Trudy to alter the message. We can see here, even though the confidentiality of the message is being maintained, no, Trudy was not able to read this message, but she sure messed it up in some way. So we would like to provide for integrity and authenticity to make sure the message only came from Alice and that it hasn't been messed with in the network. That's going to defeat some of these kinds of attacks on simple encryption schemes. How are we going to do it? Well, there are a couple of different mechanisms which are used to provide integrity and authenticity, and I'll tell you about them. The first is what's called a MAC. This is not medium access control. It's called a message authentication code. You might actually see people in networking sometimes talk about MICs for message integrity code or message integrity check. And they do that just to avoid the term MAC, because MAC means something else in the context of networks. It was all about multiple access schemes. However, in all of the security literature, MAC is what you'll see for this concept all of the time. So I'm just using MAC here, and you'll just have to know which MAC it is from the context. So what a MAC is, here's the MAC. It's been added to the message. A MAC is a small token which is used to validate the integrity and authenticity of the message. So it's an extra bit, if you like. You compute the MAC and you send it along with the message. So you can see here the message goes. The message might be encrypted if it's confidential. It might not be encrypted if it can be public, and we didn't care if everyone sees it. But in either case, you compute this MAC, this extra token, and you send it along with the message. Bob will then receive both, and he will then validate the MAC to make sure that it passes, that this check passes. He'll compute it from the message and see if it matches what he received for the MAC. If it does, then he'll say the message is legitimate. It's not been altered and it really did come from Alice, and he can then process it. An example of a MAC scheme is something called HMAC, a hashed MAC. I'm not going to tell you any of the details, but if you're, I just mention this in case so that you can relate MACs to some schemes you might see in practice written down somewhere, or you could go look it up. Now, a MAC itself is really conceptually it's some kind of symmetric key operation. And so I've drawn a picture here that should look very like our encryption for confidentiality. What happens here is that Alice starts with the plain text and she runs it through some generation function for the MAC. This is just like an encryption box, only slightly different. It's parameterized by a key, and because this is a symmetric kind of operation, Alice and Bob share the same key. So this generation function for the MAC is going to produce the MAC, and it is not a very long message like the, where are we? It's not a very long message like the message itself. It's a shorter token here, but either way it gets sent along. At the other side, Bob runs the same computation on the message, and sees if he gets the same MAC, and he uses this to validate whether the MAC check is correct, and so the message has been is authentic and has not been altered. Bob needs to know the same secret key to do this, so this key needs to be separate. So I guess just to recap here, what I'm saying is that this operation, because Alice and Bob share a key, it's going to let Bob validate that the message has not been altered and that it must have come from Alice, because Alice is the only other person who has the key, so she's the only other person who could generate this kind of MAC. However, you might notice here that this MAC does not let Bob convince someone else, say Charlie, that Alice sent him this message. And the reason is that Bob can also generate the MAC. So Charlie doesn't know whether the MAC and the message really came from Alice or whether Bob just generated it himself. So Bob can't prove anything to anyone else. So the second scheme that's used for integrity and authenticity is what's called a digital signature. It's, just the analogy is a physical written signature. The signature is going to validate the integrity and authenticity of a message. And just like the MAC here, you can see it replaces the MAC here. We're going to send it along with the message so that the receiver can check it. You might wonder what the difference is between a signature and a MAC. The difference is that the signature lets all parties validate. So you can see I don't just have Bob here. Well, I have a set of people here. They could all receive the message, check the signature, and validate that it came from Alice. An example that you might see around if you look in security schemes is RSA. encryption, RSA used to compute signatures. So just to look a little more, here is what happens in a digital signature. A digital signature is effectively some kind of public key operation. The keys again have a public and a private part to them. So you can see here Alice is going to compute a signature. Alice has her private key, only she should have it. She keeps that secret, she doesn't give it to anyone else. And everyone else who wants to check this message, such as Bob here, is going to have Alice's public key. This is Bob, but really anyone could have got this message. Because Alice is the only one who has her private key here, she's the only one who can run this signing operation and produce the signature. Because if you don't have the right private key, you generate a wrong signature, a false signature that won't verify at the other end. This signing operation is just like a public key encryption operation, only a bit different. It's producing a small fixed length output that's the signature. That signature goes along with the message, and on the other side, Bob can take them both in and do the verification operation. And if that's the case, he will know that the message which came through really did come from Alice and it really hasn't been altered. Because we're working with public key here, note that this scheme does let Bob convince someone else, like Charlie, that Alice sent in the message. He can simply send Charlie the message along with the signature and say, look Charlie, I got this. Charlie can check using his public key that the signature is correct, and then Charlie will know that Alice did in fact send that message because she has signed it. Okay, so now you've seen the signatures and MACs which are used to provide for integrity and authenticity. There's a little bit more I can tell you about them just to get towards the way that they're used in practice. The first one is pretty similar to the way we combined public key and private encryption before, public key and secret key encryption before. There's the same sort of tension as we had for confidentiality. The public key kind of integrity and authenticity using a digital signature has some keying advantages. It was more powerful, really. We could create a signature and hand it around and all sorts of people could verify it. You didn't get that with a Mac. On the other hand, it has much poorer performance. It's much slower than computing a Mac. So there's a technique that we can use to speed up signature operations in practice. And that is, they're based on the use of something called a message digest. A message digest is a relatively small, fixed length token that stands for a message. It represents the message. If we can create a message digest, then we can simply sign the digest in place of signing the message. Let me explain a little bit more about how that works. To do that, I want to tell you what these message digests are first. So I'll do that. You might hear the term message digest or a cryptographic hash. These are incredibly cool things, so you want to find out about them. They're used to speed up signatures, but they're also used all over the place for security schemes. Now, what a digest or a hash is it's just think of it as like a checksum, like a CRC or an internet checksum, only it's longer and it's secure in some way. Like a checksum, it deterministically takes in the bits of a variable length input message and it processes them down, and it mangles them in the same way as encryption does to get a pseudo-random output. This is sort of like a CRC. Your CRC, by doing the division, it's really coming up with just some set of numbers you wouldn't guess ahead of time. So they're effectively pseudo-random, even though there's a well-defined operation. They might look random to us, yet they're deterministic. They are literally a function of the message. The key property for a message digest or a cryptographic hash is that by construction, you can't find two messages that have the same hash. Now, it's not that they don't exist. Because the hash is small, say 160 bits or something like that, and messages can be much longer, there clearly must be many messages which have the same hash value, just because there are infinitely more messages around. So many of them are going to end up having the same hash value. However, it's computationally infeasible to find two messages that have the same hash value. You would have to do a tremendous amount of computing, too long for it to be feasible, as long as the scheme hasn't been cracked. So when this is true, and we have schemes for which we believe this is true today, then this digest is sort of like a magic token that is, it's like a fixed length descriptor of the actual message itself. So in some cases, we can treat it as the message. It's very useful for many things. Here's just an example of the scheme below. Here's the input message here going on, and you run it through a hash function. It's sort of like a, almost, you could imagine it's like a symmetric key encryption operation. Well, actually, let me take that back. There's no keying, it's deterministic. But it's a fairly simple, fast function which just mangles the bits. That's all I meant. You run it through this function and you get out a pseudo-random set of bits that's a fixed length, and that is the message digest. An example of a message digest function is SHA-1. You might hear SHA-1, SHA-1 is how it's pronounced. And that is 160 bits long. So any message, whether it's kilobytes through megabytes of text, can be reduced to 160 byte hash. There's still an awfully large number of hashes. There are 2 to the 160 different possible hashes. So that's sort of that's why we can't find collisions so easily, or a big factor in it. There are more hashes than we can possibly come up with, or than we could enumerate messages for, because 2 to the 160 is incredibly large. So here's how we use hashes to speed up signatures, and it's fairly straightforward. Conceptually, we'll do just what we did before. The only difference is the change in this picture is here. Instead of signing the message, we'll sign the hash of the message. That's it. This is going to help because the hash itself is fast to compute. You can go over a long message fairly quickly, and that way you only have to do the signing with a public key of a smaller portion of message, 160 bits, say. So overall, this is much faster. It's still secure because at the other side, Bob can deterministically compute the hash from the message, and the hash is standing in for the message since we don't know of ways to easily come up with different messages that have the same hash. So if I see that someone signed a hash, I could defeat this scheme if I could find a different message with the same hash. That would trick you maybe into thinking that I sent the other message. But we don't know how to do this. So we still retain security with this scheme. Okay, well, we've done a lot of stuff. There's just one more thought that I'd like to try and squeeze into your head, and then we'll understand how to send messages which are authentic messages and haven't been tampered with. The one thing we're missing is something to deal with what is called replays. Now, the point is this. Often, actually, we want more than confidentiality, integrity, and authenticity for secure messages. What? You might be thinking, more? Geez, we just added integrity and authenticity and we already had confidentiality. It seems like we're getting a lot of different security properties from a message. Yes, we are. They're all properties we need for secure systems, but we need one more. We want to make sure a message is what's called fresh, recent, or new. And that's because we don't want to inadvertently, when we receive a message, mistake some old message that might have been sent a year ago for a brand new message which someone has sent today. That's, if we do, that old message which is sent again, saved and sent again at a much later time, is called a replay. And we don't want to treat it as a new message, because if we do think it's a new message and we act on it, that might cause a lot of trouble. That might break the security of the system. Here's just an example of a replay attack, just to get you thinking about it. Maybe an overly simple example, but nonetheless. Just imagine that Trudy records all of the messages that Alice sends to Bob. And much later, Trudy's going to replay them. Now, these messages are unread. Trudy hasn't cracked the scheme. She hasn't cracked confidentiality. So she doesn't really know what the messages says in detail, but she can guess. Suppose Alice and Bob had a login. Bob asked for a password and then Alice sent the password. It's sort of a common protocol exchange for many login things. If Trudy had recorded that, Trudy could later replay them. So maybe when Bob's asking for a password from Alice, Trudy can replay this message, which, even though she can't read it, contains an encrypted version of the password. If Bob were to accept this, he would think Alice just successfully logged in. Say, great, hi, okay, what do you want to do, Alice? This would be bad. So any reasonable scheme should provide protections against this. So we want to prevent replays. How can we do this? Well, conceptually, it's not too bad. It's fairly straightforward. It gets a little more tricky in terms of implementation. just due to a few little difficulties. But to prevent replays, what you want to do is you want to provide proof of freshness in the messages. You want some way by looking at a message to be able to know that it's a new message you haven't seen before. So to solve that, here are two simple approaches. You can include a timestamp on the message so you know when it was sent, just as part of the format of the message. Or you might also include something that's called a nonce on a message. Nonce just stands for number once. So a nonce is simply a number which is on a message which you haven't seen before in a well-defined position. You might simply use a counter as a nonce, counting up. And so every time you send a new message, you might increment this counter. That way the receiver could check that the counter's been incremented, so that way they can be sure that it's a new message. You can do nonces in other ways than counters, but you get the idea that it's a number you haven't seen before. So here's Alice sending to Bob. And you can see for freshness, all I've done is we've changed the format and we've required in messages that in this case there's some kind of timestamp in there. It would be to more than a second most likely, but it's some timestamp. That way when Bob receives the message, he can know if it is a new message he hadn't seen before, depending on the time, or if it's an old message which he saw long ago. Right, so now we've gone through replays too. Sure, okay. Well, what I want you to take away here is really you've seen a bit of cryptography in action. And I'd like you to realize that we can use cryptography in different designs to provide different kinds of security properties about messages. And there are many properties. We want integrity and authenticity and freshness as well as confidentiality often. And we can provide them with different designs. This is what cryptography will give us if we do it the right way. It's very useful for secure network schemes. We'll see in a while real protocols that combine these properties in different ways depending on what they're trying to do. What I have to tell you though is that there are many pitfalls in different security protocol designs. And we've talked about this a little before, but what I would say is the way all of these different primitives are combined, it's very easy to get the combination wrong and include subtle flaws. So not only do you not want to make up your own cryptography and use approved designs, but you want to use them in an approved way so that you're using them in a safe way and you don't expose yourself to unexpected vulnerabilities. Okay, so that is integrity and authenticity for message authentication.